All right, now let's go through explicitly classifying salt solutions as acidic, basic, or neutral. Recall a salt solution is just any ionic compound, cation and an anion. So the first thing we're going to do is look at the cation and ask ourselves, okay, this cation, it's the conjugate acid of something. What is it the conjugate acid of? Is it the conjugate acid of a strong base or a weak base? Then we look at the anion. The anion is going to be the conjugate base of an acid. Is it the conjugate base of a strong acid or a weak acid? Weak acid. And that will help us determine what's going to happen when we throw this salt into water. When we take this solid ionic compound, throw it in water, will it be acidic, basic, or neutral? We need to look at the cation, the anions, and say, okay, this is the conjugate base of what? And that will help us start out. For example, aqueous KBr. If we put some solid potassium bromide into water, it became aqueous. Will that solution turn acidic? Will it turn basic, or will it stay neutral like the water was? Well, let's look at the cation. The cation K plus is the conjugate acid of KOH. You look at basically what the cation is, add OH to it, OH minus to it, and decide is that a strong base or a weak base. Well, that's a cation of KOH. That's a strong base. Therefore, K plus is neutral, because the conjugate acid of a strong base is neutral. Br minus, well, that's bromide. We know that's the conjugate base of HBr. Take your anion, add a proton to it, and see what type of acid that was. Bromide is the conjugate base of HBr, a strong acid, therefore bromide is neutral. Well, if our potassium is neutral, our bromide is neutral, that means KBr is neutral. You throw KBr into water, and the water essentially, the pH does not change. Stays neutral. All right. Next example, let's look at NaC2H3O2, sodium acetate. Let's throw that in the water. Question, is that water going to become acidic, basic, or will it stay neutral? Well, let's look at sodium. Well, sodium we know is a conjugate acid of sodium hydroxide. Sodium hydroxide is a strong base, so if sodium is the conjugate acid of a strong base, it is neutral. So we don't have to worry about the sodium changing the pH. Acetate is a conjugate base of acetic acid. We know acetic acid is a weak acid. Therefore, acetate is the conjugate base of a weak acid, and the conjugate base of a weak acid is a weak base. So acetate is a weak base. So if sodium is neutral, but acetate's a weak base, we know when we throw it in water, the solution will turn basic because we have a weak base. Sodium acetate is weakly basic. Okay. What about our next one? NH4Br, ammonium bromide. What happens when we throw it into water? Will it turn acidic, basic, or remain neutral? Well, what's our acid? What's our cation? NH4 plus is the cation. Well, it's the cation. What is the base that NH4 comes plus? What accepted a proton to become NH4 plus? The answer is it comes from NH3. The conjugate base of NH4 plus is NH3. Another way of saying that, the conjugate acid of NH3 is NH4 plus. So NH4 plus is the conjugate acid of NH3. NH3 is a weak base. So NH4 plus is the conjugate acid of a weak base. NH4 plus is a weak acid. Okay. Bromide, our anion is bromide. Okay, well we know bromide is the conjugate base of HBr. Just throw a proton on it. We know that's a strong acid, therefore we know bromide is neutral. So if bromide is neutral, putting it in water won't affect the pH. NH4 plus is a weak acid, which means if you put ammonium bromide in water, the water turns acidic. The water is a little bit more acidic because the NH4 plus is going to release some protons into water. All right, okay. That looks pretty straightforward. What about NH4CN? What about ammonium cyanide? Well, let's take a look at it. The first thing we find, well, cyanide, Cn minus, is the conjugate base of HCN. HCN is a weak acid, therefore cyanide is going to be a weak base. So cyanide wants to turn the water basic. Ammonium, well, we already found out from above, ammonium, NH4 plus, wants to turn the water acidic. All right, I have written down right here that it turns out that the Ka value for ammonium, we had that already, is 5.56 times 10 to the minus 10th. Kb for cyanide is right there. And wait a minute, we've got a problem. Ammonia is acidic, cyanide is basic, so the cyanide ion wants to turn the water basic. The ammonium ion wants to turn the water acidic. Which way is it going to it's going to turn? If one thing wants it acidic, one wants it basic, what's going to happen to the water? Truth is, those two have to duke it out. Which is the question is ammonium a stronger acid than cyanide is a base? Which is the stronger acid compared to the base? Is this a stronger acid than this is a strong base? We look at the Ka and Kb values. You realize for ammonium, 5.56 times 10 to the minus 10th is a very low equilibrium constant, which means it really doesn't want to turn anything very acidic. It's not going to release much H+. The Kb for cyanide is 2.0 times 10 to the minus 5th, which is a larger equilibrium constant than this one, which means cyanide, having a larger equilibrium constant, affects the solution more than ammonium does. Since cyanide wants to turn it basic, this ammonium cyanide ionic compound will turn the water basic because cyanide is a stronger base than ammonium is as strong an acid. Right. That's a bit complicated, and so we're not going to delve too much into this. Know what will happen here. Definitely know about our first examples up here. And when you have a weak acid and weak base as your conjugate acid bases for your salt, it gets a little trickier. You have to look at the Ka compared to the Kb value, see which is the larger value, and that will determine whether it's acidic or basic. The Kb is larger than the Ka, therefore the base form is going to change the pH basic compared to the acid form. Doesn't have enough power to turn it as acidic as the base has to turn it basic. All right. A few last things on this video right here. Just some stuff to be aware of, some more definitional types of things. 5, the strongest acid that can exist in water is H3O+. The strongest base that can exist in water is OH-. What does that mean? That means if you have an acid that is stronger than H3O+, then that acid will dissociate into, when it's put in water, to form H3O+. Example, HCl. We've done a whole bunch of reactions with HCl. HCl is a strong acid, therefore if you put HCl in water, it dissociates 100% and forms H3O+. HCl is a strong acid, dissociates 100% to form H3O+. It is a stronger acid than hydronium, therefore dissociates and forms hydronium. Acetic acid is a weak acid. You put it in water and you have quite a bit. Acetic acid is HC2H3O2. You put that into water and you still have lots of HC2H3O2s existing. This is a weaker acid than hydronium, so it can exist in water with the proton on that anion, since it's weaker than H3O+. H3O+ is the strongest acid that can exist in water. If you throw in a acid into water that is stronger acid than H3O+, such as HCl, such as HBr, such as H2SO4, that acid will dissociate to form H3O+. The strongest base that can exist in water is hydroxide. You throw in a base that is stronger than hydroxide, and it will dissociate to form hydroxide. Okay. And so the last thing in this video is a table from your book. Pretty important, especially if you go on to organic chemistry. This type of table becomes very important. You're looking at acid strength versus base strength here in this table. So note, let's look at this column here. Here are our acids, HCl, H2SO4, our strong acids. We classify H3O+ as a strong acid because it's the strongest one that can exist in water. But no, this is acid strength increasing, which tells us HNO3 is a stronger acid than H3O+. H2SO4 is stronger. HCl is stronger than these acids. All right. So then as we go, these are our strong acids. As we go to weaker acid, we have HSO4 minus, HF, acetic acid right here. These acids are getting weaker as we go down the table. These acids get weaker and weaker. We note that cyanide, a pretty darn weak acid, Ka is on the order of 10 to the minus 10th. NH4+, these are weak acids here. And so then our weakest acid is water, and these, well, HS and OH minus, we classify those as bases, so we don't even worry about their acidic properties for this class. All right. But we look at these are weak acids. Here we have the conjugate base of these acids. Note HCl is a strong acid. Its conjugate base is Cl minus. The conjugate base of a strong acid is neutral. Okay. So these guys are fairly neutral. HSO4 minus is a little weird. We will discuss that in a bit. HSO4 minus has issues. But these guys are essentially neutral. In fact, HSO4 minus, they put it neutral. It's actually a little bit acidic. All right. So here are our conjugate bases. They tend to be neutral. As we went down the acid, these acids got weaker and weaker and weaker. Note, the conjugate bases get stronger and stronger and stronger. So, the conjugate base of a strong acid is neutral. The conjugate base of a weak acid is a weak base. But the weaker the acid, the stronger its conjugate base. Base strength is increasing as we go down the table. So while F minus is a weak base, because it's the conjugate base of the weak acid HF, this is a weak base. Cn minus is a stronger base than F minus. Note, cyanide ion is still a weak base. Fluoride ion is a weak base, cyanide ion is a weak base, but cyanide ion is a stronger base than fluoride ion. It's still weak, but it is stronger than fluoride. So, as you go down the table, acid strength gets smaller and smaller and smaller. Base conjugate base strength gets larger and larger and larger. So, the weaker the acid, the stronger the conjugate base. The biggest problem you're going to have is you're going to confuse it with the statements we made before. The conjugate base of a weak acid is a weak base. These are all weak acids. Here are their conjugate bases. These are all weak bases. The conjugate base of a weak acid is a weak base. However, the weaker the acid, the stronger the conjugate base. All right. That's enough for this video. We will continue on with these acids and bases in the next.